Think for a moment about a single number, 27. What does that mean to you? Is it the temperature outside, a person's age, the number of unread emails in your inbox, or how many apples are in a basket? The bare symbol, 27, is the same in all those cases, but its meaning changes wildly depending on context. And that difference between raw symbols and their meaning is exactly what we call semantics. When we talk about data, people often focus on format, JSON versus CSV, rows versus columns, ints versus floats. That's important, but format is only syntax. It tells you how the data is written down. Semantics answers a different question. What does the data actually mean? What real-world quantity or concept does that 27 stand for? Let's start with a simple distinction. Syntax versus semantics. Syntax is grammar, the shape of the data. Semantics is the interpretation, the story we tell about that shape. If syntax is the alphabet, semantics is the language those letters spell out. Why does this matter? Because many of the trickiest problems in data are semantic problems, not formatting problems. Imagine you receive a dataset full of temperatures. Some rows are in Celsius, others are in Fahrenheit. The numbers alone don't tell you which is which. If you treat every value as degrees, you can build a model or produce a chart, and it will be quietly, disastrously wrong. The data looked fine, the semantics were different. So how do we attach meaning to data? There are two broad mechanisms. First, explicit semantics, the things we write down as metadata, labels, units, data types, field descriptions, or schema. Explicit semantics are the signs we intentionally leave: temperature Celsius, date of birth, customer ID. They are the promises the data makes about itself. Second, implicit semantics, the meanings that live in practice, habits, or context. For example, a column named score might mean different things in different systems: test score, credit score, similarity score. If you only look at the numbers and the column name, you might guess incorrectly. The data's meaning can be implicitly encoded by how it's collected, who collected it, and how it's used downstream. Good explicit semantics is like good labeling on a supermarket shelf. It helps everyone pick the right item. Good implicit semantics is the shared understanding between shelf stockers and shoppers, the conventions that let you reach instinctively for flour without reading the fine print. Both are necessary. Neither is fully reliable on its own. Let me make this a bit more concrete with 3 examples. First, units. A single column, length, can be meters, feet, or miles. If 2 datasets use different units and you mix them without conversion, you've got nonsense. Units are a form of explicit semantics. They're easy to check if someone remembered to declare them. Second, identifiers. Consider a field called id. In one system, it might be a national ID number. In another, it might be an internal database key. And in a third, it might encode the user's region. These IDs are syntactically similar, strings or numbers, but semantically completely different. Confusing them breaks joins, lookups, and reasoning. Third, labels in machine learning. The same picture of a dog might be labeled dog in one dataset and golden retriever in another. Both are true, but they encode different levels of specificity. If you train a model on mixed granularity without reconciling semantics, the model will learn a muddled concept. So what do we do about this? There are 3 practical moves data professionals make to manage semantics. 1. Be explicit. Add schema, units, data dictionaries, human-readable descriptions, and provenance. If a column is temperature, annotate it, Celsius or Fahrenheit. Measured at what time? Which sensor? Who collected it? These small clarifications are enormously powerful. 2. Standardize. Adopt ontologies, controlled vocabularies, or shared naming conventions. The more that different datasets agree on what a field means, the easier it is to combine and reuse them. Standards aren't glamorous, but they scale. They let small teams compose into big systems. 3. Test and validate by meaning. Don't only test types and ranges, test expectations. If age has a negative value, or date of birth is in the future, flag it. If the distribution of a field shifts dramatically over time, that could be semantic drift. the meaning or measurement process changed. This last idea, semantic drift, is crucial in long-lived systems. Data that once meant one thing can creep to mean another thing because of a sensor replacement, a change in a form, or a new business process. Your code might still run, your dashboards might still show numbers, and yet your decisions are being fed with a different meaning than before. It's also helpful to think of semantics as a mapping problem. Data is notation. Semantics is a map from notation to reality. The better that map is specified, the fewer surprises you'll encounter. In some environments, that map is formal, a schema, an ontology, a contract between teams. In others, it's tacit and fragile. Your job as a data creator or consumer is to make that map as clear and robust as you can. Before we close, one more perspective. Semantics is not just for humans. Machines need semantics too. When we build algorithms, from simple data pipelines to complex machine learning systems, we rely on assumptions about what inputs mean. If those assumptions are wrong, the algorithm's output is meaningless, or worse, misleading. Garbage in, garbage out is as much a semantic statement as it is a syntactic one. To finish, return to that number 27. The number itself is just a symbol. Semantics is the act of saying what it stands for. Make that act intentional. Make it explicit when you can, and curious when you can't. Because clarity about meaning is how data turns into understanding.